Hi, it's Cameron Gibbleu again, and this time I'm talking about how the first stars formed. If you're taking big history, this talk will help you understand the units on the Big Bang and star formation. The universe was almost the same everywhere in its early days. Same mix of particles, same density, and so on. For example, we can directly observe the cosmic microwave background radiation, which carries the fingerprint of what the universe was like 380,000 years after the Big Bang, and we find that it is 99.999% uniform. This means that every part of the universe was almost completely identical to every other part of the universe, which is much different than what things are like now if you think about it, since there's an unimaginably big difference between, say, the surface of the Earth and the emptiness of intergalactic space. The universe was nearly the same everywhere in its early days, but the universe was never 100% uniform, as you can see from the fact that even the cosmic microwave background has small variations in its temperature, as shown by the different colors in this image. This is important because it means that gravity could go to work and make those non-uniformities grow. How does it do that? Think about a region of space with just a tiny bit more matter in it than the area around it. That region is going to have just a little bit more gravity than the surrounding area, and that means it'll attract matter from the surrounding area. So the denser areas, the areas with more matter, pull in matter from the less dense areas. The rich get richer and the poor get poorer, which is a theme you'll probably notice happening in other parts of history too. But the trend started with the universe itself. As the universe started getting clumpier and lumpier, as more and more matter got pulled toward the denser regions, and the slightly emptier regions became even emptier, those denser areas formed what we call protogalaxies, the building blocks of today's galaxies. In those protogalaxies, the first stars formed. We've never directly detected one of that first generation of stars, so we have to make educated guesses about how they formed. To do this, we apply basic laws of physics to what we already know about the conditions of the universe at that time, and use computer simulations to work out some of the toughest details. New astronomical observations in coming years, such as those that will be done by the James Webb Space Telescope, the Hubble Space Telescope's successor, should be able to test whether some of these educated guesses are correct. But for now, here's the best of our informed speculation about how the first stars formed in early protogalaxies. Immense clouds of gas within those protogalaxies would have collapsed under their own gravitational pull, until the centers of those clouds became quite dense and hot, as pictured in this image of a computer simulation of the process. Eventually, the center would become so hot that nuclear fusion would start, and when fusion starts, you officially have a star. Now, at this relatively early point in the universe's history, there were virtually no elements in the universe except hydrogen and helium. So the first stars had to have been made of hydrogen and helium and essentially nothing else. The first stars would have been very massive, probably around 100 times the mass of the Sun on average, because a gas cloud made only of hydrogen and helium can't collapse under its own gravity unless there's many times the mass of the Sun's worth of material in it. We can say this confidently not because we've directly observed the first stars, which we haven't, but because we know about the chemistry and physics of hydrogen and helium. This is a great example of how we can use knowledge of chemistry and physics to help us understand astronomy. In addition to being big, both in terms of mass and in terms of volume, the first stars would have been very short-lived. Very massive stars live shorter lives because they burn so furiously and release so much energy, so the first stars would also have been very short-lived. We're still talking about lifetimes of millions of years, but compared to the billion and trillion year lifetimes of most stars in the present universe, a stellar lifetime that only lasts a few million years is actually quite short. This explains why astronomers have not yet detected the original stars. They were huge, they lived fast, and they died young, and none of them are around anymore. In order to see them, we would have to look very far back in time by looking very far out into space, and our observing technology just isn't good enough for that yet, though NASA's planned James Webb Space Telescope may be able to do it. The remnants of the first stars may still be with us, though, in the form of black holes that these stars became when they collapsed in on themselves at the end of their lives. And their remnants are definitely still with us, in the sense that we are, in part, their remnants. These first stars made some of the first elements that were heavier than helium, and in particular, some of the carbon and oxygen in our bodies was probably manufactured by fusion inside these stars, with the rest of the carbon and oxygen within us being made by later stars. A typical galaxy in today's universe is the result of the merging of many thousands of the protogalactic gas clouds in which the first stars formed, and the formation of new stars continues in present galaxies. Astronomers estimate that around one new star is born every year in our own Milky Way, in regions such as the ones pictured here, and some galaxies, such as this one, produce new stars at much higher rates.